Assalamualaikum warahmatullahi wabarakatuh. So today our group will be presenting our wireless local area network design and performance analysis for CS1 building. Our team consists of me, myself, Idina Humaira binti Syara Azami, Muhammad Firhat Hakimi, and also Nick Maisara. We will start with Chapter 1, Introduction. For background, wireless local area network are essential infrastructure that enables wireless internet access primarily operating on the IEEE 802.11 Wi-Fi standard. So within the UITM ecosystem, students and staff rely heavily on this infrastructure daily, connecting on the dedicated SSIDs such as UITM Wi-Fi students, EduRoam, and UITM Wi-Fi staff. The CS1 building serves as a critical academic hub. It houses the classroom, lecture halls, administrator's office, and also lab. So which all demands seamless and high-speed reliable connectivity. Next, for the problem statement, we have noticed that the current network infrastructure in CS1 building face some major challenges. First is network dead zone. We see inconsistent signal coverage across certain classroom and also lab. This leads to a dead zone that frequently disrupt lectures and also research. So next is high user density. During peak hours, thousands of devices attempt to connect simultaneously, creating a massive traffic congestion that overwhelms the active hardware. Third is security vulnerability. With so many users, insufficient security protocols leave the network exposed, which putting the sensitive university and student data at risk. To address the problem that mentioned, our project has set four objectives. The first one is to design a wireless local area network that provides a reliable wireless connectivity for users in CS1. Next is to configure wireless device, access point, and network settings that enables effective communication. Third is to implement wireless security mechanism to protect the network from unauthorized access. And lastly is to evaluate the functionality and performance of the wireless LAN through connectivity and also network testing. So the significance of this project is that a well-designed wireless LAN is the backbone of the modern smart campus. So this project helps to improve wireless connectivity, supports teaching, learning and also research, and also enhance the network security. We are moving on to Chapter 2, Literature. Wireless LAN connects local device wirelessly using radio wave. Over the year, Wi-Fi standards have evolved to meet higher performance demands, transitioning from legacy standards like 802.11n to 802.11ac, which is Wi-Fi 5, and now to 802.11ax, Wi-Fi 6, which provides much faster data rates and handles high client density far more efficiently. To optimize this performance, our design utilizes several modern features, which is MIMO, multiple input, multiple output to increase throughput, beamforming to focus signals directly towards active user rather than broadcasting in all directions, quality of service QoS to prioritize critical academic traffic, and finally, robust security protocols like WPA2 and WPA3 to protect wireless transmission. To address the problem that mentioned, our project has set four objectives. The first one is to design a wireless local area network that provides a reliable wireless connectivity for users in CS1. Next is to configure wireless device, access point, and network settings that enables effective communication. Third is to implement wireless security mechanism to protect the network from unauthorized access. And lastly is to evaluate the functionality and performance of the wireless LAN through connectivity and also network testing. So the significance of this project is that a well-designed wireless LAN is the backbone of the modern smart campus. So this project helps to improve wireless connectivity, supports teaching, learning and also research, and also enhance the network security. This network design also incorporate software defense such as firewall, anti-malware, anti-spyware, and also IDS and IPS. Firewall monitors and filters traffic based on security rules to prevent malicious intrusion. So for anti-malware, it protects the mobile device from worms, ransomware, and also Trojan in a public Wi-Fi environment. As for anti-spyware, it prevents the theft of sensitive logins, credentials, and personal student information. For IDS and IPS, it detects and prevents cyber attacks.
Assalamualaikum everyone. Now I'll be presenting Chapter 3 of our group project, We Learn Design for FSKM CS1. This chapter covers how we design the wireless network for Flow 2 and Flow 1 of the building from performance requirement all the way through the logical network culture. Okay, now let's start with Flow 1 requirement. We set a minimum signal strength of negative 65 dBm and a signal to noise ratio of 25 dB, which is needed to support higher order modulation scheme like 256 QAM. Flow 1 has 5 seminar room with roughly 20 to 25 users each. Mostly BYOD, that is bring your own device, laptop and smartphone. Based on estimate of 2 to 3 Mbps per user for LMS access and video conferencing, we calculate a minimum of requirement of 25 Mbps download and 60 Mbps upload. Okay, we also require at least 5 access points to cover both wing and the foyer without dead zone, along with round trip latency under 20 ms and near zero packet loss to support real-time collaboration tools during session. Now we go through with the network requirement for Flow 2. Flow 2 share the same baseline signal and NSR target, but has a higher data rate requirement, 80 Mbps download and 65 Mbps upload. because it has a 12 classroom and that are fully BYOD, with a higher total device count than floor 1. We propose a minimum of 4 access points to cover left wing and right wing, total room, and the central corridor. Now we go through we're moving to capacity planning. Okay, for floor 1, has a mix of device type: 8 desktop computer in the office area, plus 60 laptop, 80 smartphones, and 10 tablets brought in by student and staff. About 161 devices in total. Okay, floor 2 is purely BYOD with 0 fixed computer, 100 laptop, 120 smartphones, and 10 tablets, totaling around 230 devices. As the chart show, smartphones are the dominant device type on both floor, and the floor 2 is higher demand floor overall. Okay, for coverage, each floor cover approximately 4,200 square meters based on the agricultural floor plan at scale 1 to 400 scale. This figure include all enclosed room, corridor, and service area, but exclude external walkway and open atrium space. Because the building has a V-shaped layout with concrete wall and partitions, our access point planning has a account for signal propagation across both wing and wide central foyer, while still meeting the negative 65 dBm and 25 dB SNR target everywhere. Now, we go to the floor 1 AP placement. Okay, for floor 1, we're proposing 5 access points. AP1 sits in the foyer and act as a central roaming anchor between the two wings. AP2 cover the right wing, but bilik seminar 4 and 5 plus the office area, counter, pejabat and bilik pegawai. AP3, AP4, and AP5 are each dedicated to bilik 3, 2 and 1 respectively. So every seminar room gets strong, uncongested coverage even with a multiple session run in the same time. Okay, now we go through the floor 2 AP placement. On the floor 2, we're proposing 4 access points. AP1, AP2 split the 5 left wing classroom between them. AP3 sits centrally near the storeroom and double as the roaming anchor between the two wings. AP4 is positioned in the right corridor to cover all 7 total rooms, T120 through T126. The unused storeroom doesn't need dedicated coverage since they have no connected devices. Okay, now we go through with the access point specification. As for the actual hardware, we selected the Cisco Catalyst 9105 AXI as a Wi-Fi 6 access point. It supports 802.11ax, dual band 2.4 and 5 GHz and 2x2 MU MIMO with OFDMA, which matter because OFDMA lets the AP serve many BYOD devices in parallel rather than one at a time, cutting down waiting time during busy class periods. It's also WPA3 Enterprise with 802.1x radius authentication for security and only needs 802.3AF PoE power, which keeps our switch requirements simpler and more cost effective. Okay, now this is our logical network diagram. Okay, internet access come through in the ISP. Enter via the Cisco ISR 4331 router for LAN for WAN routing and NAT, and pass it through the ASA firewall for stateful packets inspection before reaching the internal LAN. At the core, multi-layer switch handle all the inter-VLAN routing and act as a default gateway. Each floor has its own switch with power and connected to the access point. Okay, and then we are segmenting traffic into 5 VLANs, and that is staff, student, guest, printer, and management. For example, guest traffic stay completely isolated from the internal campus LAN. Okay, now we go to the special consideration. This is special consideration behind our design. First, the backbone use the now for the backbone use a 3-layer hierarchical design. So routing is centralized and future floor can be added without a major redesign. Second is our hardware choices. The router, firewall, code switch, and access switches, access point, were all enterprise grade to ensure reliability and performance. And the third one is security. Security is handled through multiple layer firewall, access point list, VLAN isolation, WPA3 interface, authentication for staff and student SSID, and AES CCMP encryption across all wireless traffic. Now continue fourth. We give priority access point placement to high demand area, like dedicated 1 AP per seminar room, cluster on floor 1. So C-terminus section don't compete for bandwidth. Now 5A for performance and QoS. We split the load between 5 GHz band for high throughput tasks like streaming and 2.4 GHz for broader coverage on all the devices, using non-overlapping channel to minimize interference. And 6 is the design is scalable. More access points can be added to the existing switches, and the VLAN can be provisioned at the core without needing a dedicated wireless controller hardware, since the 9105 AXI has a embedded controller built-in. That's all for me. Thank you.
Assalamualaikum and hi, my name is Nikmesara binti Muhammad Kaizir. Now I will present Chapter 4, Result and Analysis. Flow 1, existing wireless LAN signal strength. So, dead zone detected at bilik seminar 1 and 2 with signal strength below minus 80 dBm and weak coverage observed at bilik seminar 3, bilik seminar 4 and surround due to wall attenuation, and good coverage is limited to the foyer and counter where the two existing AP are located, and impact unstable wireless connectivity and failure to meet the requirement more and equal to minus 65 dBm coverage for student learning area. Next is floor 1, proposed wireless LAN signal strength. So 3 additional AP deployed in bilik seminars 1, 2 and 3 using the 5 GHz band, and dead zone eliminated with signal strength improved to minus 45 dBm to minus 60 dBm, and all seminar rooms now achieve the required more and equal to minus 65 dBm coverage for reliable wireless connectivity and administrative area were intentionally excluded to optimize deployment costs. So this is floor 2, existing wireless LAN signal strength. So critical dead zone detected in the left wing SL13 to SL17 with signal strength below minus 80 dBm, and existing AP located at the central staircase and right corridor cannot penetrate thick lab walls. So weak coverage observed in surrounding corridor and adjacent room. So impact unstable connectivity, higher packet loss, and poor performance for program and lab activities. Next is floor 2, proposed wireless LAN signal strength. So 2 additional AP was added in software lab SL14 and SL16. So dead zone eliminated, providing strong signal coverage of minus 45 dBm to minus 60 dBm across the left wing lab, and all lab area now meet the required more and equal to minus 65 dBm signal strength for reliable connectivity, and administrative area were intentionally excluded as they use separate staff Wi-Fi infrastructure. Next, we go to signal noise ratio (SNR). Existing design, 2 APs, strong SNR only near foyer and counter, and left wing, bilik seminar 1 and 2 has poor SNR due to limited AP coverage, wall attenuation, and RF noise impact. So proposed design, 5 AP added AP in bilik seminar 1, 2 and 3. So SNR improved to more than 30 dB across academic area, and wake or orange coverage area are significantly reduced. So the impact, higher signal noise ratio is more stable connection and fewer retransmission, and then that can support online learning, video streaming, and file transfer. So we move to floor 2, signal to noise ratio (SNR). Existing design, 2 AP, acceptable SNR is limited near the center staircase and right wing. So left wing experienced poor SNR due to no nearby AP coverage, wall attenuation, and then increased RF noise impact. So proposed design, 4 AP added AP inside software lab, and SNR improved to 30 to 40 dB across the lab area. So the impact, improved SNR provides more reliable connection, lower packet retransmission, and better performance for high density lab activities. Okay, this is network performance analysis for floor 1 and floor 2. So for packet loss, for existing design, higher due to weight coverage and signal attenuation, and for proposed, we reduce with improved signal and strength. Second, latency, higher delay due to unstable connection, and we propose with optimized AP placement. And third is network jitter, inconsistent packet transmission, and we propose with more stable data delivery. And fourth is packet retransmission, increased due to weak RF condition, and we propose with reduced transmission error. And for uptime, coverage gap cause unstable connectivity, and with proposed design, we provide reliable connection. And fifth is throughput. For throughput, existing design limited performance in uncovered area, and we propose we can improve capacity across academic area. Last is chapter 5, recommendation and conclusion. So there is 4 recommendations. First is automatic RRM, optimized AP channel and power allocation to reduce interference. Second is Wi-Fi 6 or Wi-Fi 7 upgrade to provide more spectrum and improve future scalability. Third is directional antenna to improve RF control in high density area. And fourth is band and client load balancing to distribute user efficiently and maximize 5 GHz performance. So for conclusion, proposed wireless LAN design successfully improved coverage and signal quality on both floor. So signal strength improved for floor 1 from 65% to 84%, and for floor 2 from 77% to 94%. So redesigned wireless LAN provide more reliable, scalable, and high performance connectivity for academic activity. And that's all from us. Thank you, sir, for listening and giving us this opportunity to present our project. We really appreciate and for your time and feedback. So thank you.